Hey everybody, this is going to be coming from section 3.3 in your textbook, and it is all about the properties of logarithms. Feel free to follow along on the notes handout or just to take your own notes how you deem fit. So first of all, we need to actually remember what a logarithm is and how it works. Where a is greater than 0 and a does not equal 1, log base a of x equals y if and only if a to the y equals x. You've seen this already. This is how you rewrite logarithms from log form into exponential form. An easy trick, if you will. It's not really anything to do with the why of what this definition is, but we figured out that these are inverses, right? So it's basically like if you're trying to solve for x, like this is how you get x alone. You rewrite it where the base has now become the base of the exponential function. X is the exponent, x is the answer and y is the exponent. So we need to keep this in mind through all of the different properties that we talk about today. Next week we're going to be doing a lot of actual solving exponential equations and solving logarithmic equations, but in order to do that you must know their properties, so that way you can simplify those equations. Either you're going to need to condense them into one logarithm, or it might make sense to expand them into multiple logarithms. It generally involves rewriting it from logarithmic to exponential or exponential to log. It totally depends on the situation. Either way, you're going to need to know the different properties. You have definitely talked about these properties before. You should have done them in Algebra 2. So there's 4 basic properties. I call them the basic properties anyway. And the first one is that log base a of 1 equals 0. Let's talk about why this is the case. Really, if you rewrite it in exponential form, it makes complete sense. Because if I rewrite it in exponential form, that's going to say a to the 0 equals 1. So, of course, that makes sense. So that's saying the log of anything, the log that has any base of 1 is always going to equal 0. Because anything to the 0 power equals 1. Also, you're going to have log base a of a, and that's going to equal 1. Again, if you rewrite it in exponential form, this makes sense. A to the 1 equals a. That's just true. That's why it's a basic property. All right, third basic property. Log base a of a to the x power equals x. Well, again, we can think about this if we write it in exponential terms. If I move that base over here, a to the x equals a to the x. So some people kind of like to think of it as like, oh, if you have log base a of a, basically that cancels out and you just get x. Which is kind of true. I mean, that it does equal x, but the reason it equals x is because of this over here. One more basic property. If the log base a of x equals log base a of y, that means that x must equal y. So they have to have the same base. But if they have the same base and they equal each other, then that means that the x and the y must equal each other as well. Let's do some simplifying examples before we move on to the more interesting properties. All right, let's suppose I ask you to simplify log base 4 of 1, log base square root of 7 of square root of 7, and let's do log base 6 of 6 to the 20th power. So I kind of would like you to pause the video at this point and just see if you can try these three using the 4 properties that we wrote down. So go ahead and do that, please. Okay, hopefully you tried that on your own before you hit play. But this is going to equal 0 because 4 to the 0 equals 1, so that equals 0. This one is going to equal 1 because the square root of 7 to the first power is going to give you the square root of 7. And this one's going to equal 20. Again, log base 6 of 6, it's essentially the 20 is what's left over. Okay, now there's 3 main properties that you would have learned in Algebra 2. So these are really important, and these are probably the ones that you were thinking of when you saw the title, Properties of Logarithms. The first one is the product property. It tells us that log base A of u times v equals log base A of u plus log base A of v. This also actually is true for natural logs. You've learned a little bit about natural logs at this point. They're just logarithms with a base of e, so they're still logarithms. They follow all the same rules. So if I have the natural log of u times v, I'm going to have the natural log of u plus the natural log of v. Notice that the uv is being multiplied like as a function of the logarithm. The next one is the quotient property. And that is log base A of u divided by v equals log base A of u minus log base A of v. And again, we could write this with natural logs as well. The natural log of u over v is going to equal the natural log of u minus the natural log of v. And then one more that is called the power property. And that is where you have an exponent on what is inside the function. So the log base A of u to the n power. So u is what is to the n power, not the whole logarithm. It's u that is to the n power. You actually take that exponent and move it to the front. Again, I'm hoping that this looks familiar, that you've seen this before. I can write it as a natural log. Natural log of u to the n is going to be n natural log u. You just move the power to the front. Now, hopefully, all 3 of these rules kind of remind you of something else. And I'm sure you talked about this before. But these are very similar to exponent rules. Remember, when you multiply 2 things that have the same base, you add their exponents. When you divide 2 things that have the same base, you subtract their exponents. Those are kind of the main 2 for those. And then also when you have like a power to a power, you multiply. When you have x squared to the 3rd power, you multiply the 2 and the 3. That's very similar to the power property. This makes sense because these are just another, like they're inverses of exponential functions, right? So they follow very similar rules. Now, if you would really like to see why that is, like why this is the way it is, I would recommend that you check out my next video that I'm going to post that's going to give you the proof of these, or you can also find out on page 258 in your textbook. It gives you the proof of mathematics. For now, I'm just going to give you the properties and use them, and if you want to explore why, please see the other video or check out page 258. Let's do some examples. I mentioned at the beginning of this video that we're eventually going to be solving equations that are involving exponential functions or logarithmic functions, and that sometimes you're going to have to expand those expressions before you can solve them, and sometimes you have to condense them. Let's start off with doing some expanding to practice. So in Algebra 2, I think probably the directions you would have said, rewrite this as a sum or a difference of logarithms. And that is exactly the same thing as this. When I'm asking you to expand the log expressions, I'm asking you to rewrite this as a sum or a difference, or perhaps a product with the exponents. Okay, so first of all, I notice that these are all being multiplied to each other, and so I need to split them up with plus signs. It's going to be log base 4 of 5 plus log base 4 of x cubed plus log base 4 of y. Notice that all three of those have log base 4. That's how it works. It has to have the same base. The only thing that's left that I notice here is that cubed right there, that cubed, it needs to move to the front. That was the power rule. So I'm going to have log base 4 of 5 plus 3 log base 4 of x plus log base 4 of y. And that's the answer. I asked you to expand it, and it is now fully expanded. Let's try another one. Let's say that you have the natural log of the square root of 3x minus 5 all over 7. Once again, natural logs are logarithms. They just happen to have a base of e, so all of the rules stay the same. I notice this time that I have a quotient happening. I know that that means I'm going to be subtracting. So it's going to be the natural log of the square root of 3x minus 5 minus the natural log of 7. Now, one thing that I hope you remember, or that you will now remember, is that the square root is the same thing as raising something to the 1/2 power. That's going to be important in this section. That's going to come up a good bit. So I rewrote that square root so that it was 3x minus 5 all raised to the 1/2 power. And now I can follow the power rule and take this and move it to the front. So 1/2 the natural log 3x minus 5 minus the natural log of 7. And that is actually the final answer. One thing that I probably should mention, notice there's nothing I can do with this 3x minus 5. The product rule and the quotient rule, it has to be a product inside the parentheses or a quotient inside the parentheses. It doesn't go the other way around. So there's the answer for that. I would love for you to try one on your own. So go ahead and try this one. Again, I want you to expand it. Let's say that we have the log base 3 of 4x squared all over the square root is 7. Go ahead and pause the video now and try to work this one out on your own. Pause it. Go ahead. Do it. Try it on your own. And there is the final answer. Log base 3 of 4 plus 2 times log base 3 of x minus 1/2 log base 3 of 7. Notice I kind of just went in order. The two things that were being multiplied on the top end up with a plus sign, and what was being divided is then subtracted. Now let's try to kind of go the other way. Let's suppose that I give it to you expanded, and instead I want you to condense it. Condense each logarithmic expression. The first one we'll do is 1/2 log of x plus 3 log of x plus 1. Notice neither of these have a base specified, but that means that these must be common logarithms, so their base is 10. As long as their base is the same, you can follow the different logarithmic properties. We got to make sure the base is the same. I see a couple of things here. I see some numbers in the front. I know that that's going to become an exponent. Remember, I'm working backwards here. I also see a plus sign, which means I'm going to be changing things into a product. If I'm condensing the logarithmic expression, that means I'm putting it together into one log. So I'm going to have log, And then I'm going to just go ahead and put like a bracket or something to show all these things are going together. I'm going to have x to the 1/2 power times x plus 1 to the 3rd. So see how I moved the exponent up and then I multiplied the two things. I'm just going to rewrite this with a square root sign to show that you can also write it this way. But both of those are technically the same thing. Alright, what if we have 2 natural log of x plus 2 minus the natural log of x? Okay, so once again, I see I have an exponent that needs to go back up. The 2 needs to go back up. I also see I have a subtraction sign, which means I'm going to do the quotient property. It's all going to be natural log. They both have the same base. So natural log of x plus 2 squared divided by x. And that's it. That's the answer. That's as far as I can go. One more together. Let's suppose that I have 1/3 times the quantity of log base 2 of x plus log base 2 of x plus 1. I know that we have this exponent here in the front, but I'm not going to move it just yet. Let's follow order of operations. All of this is in parentheses, so I should probably deal with that first. I'm going to leave the 1/3 in the front, and I'm going to go ahead and combine these two. So log base 2 of x times x plus 1. Okay, so x times x plus 1 is going to be on the inside of the function, and now I'm going to take the 1/3 and move it up. So I'm going to have log base 2 of x times x plus 1 all to the 1/3 power. And then there's one more way that I could write it. I would be okay with that answer. But if I'm writing it in terms of roots, I'll have log base 2 cube root of x times x plus 1. There it is. Why don't you go ahead and try one on your own, please? 2 times the quantity of log of x plus 3 minus 2 log of x minus 2. So once again, go ahead and pause the video and try this one on your own. I went ahead and wrote this answer in two ways. I have the log of x plus 3 all divided by x minus 2 squared, all squared. Or if I go ahead and actually square both the numerator and the denominator, I have what I circled here. The log of the quantity of x plus 3 squared divided by the quantity of x minus 2 to the 4th. There's one more kind of formula or property that you need to be familiar with. This next thing is called a formula, though I mean it really is kind of a property, but it's a way that you can change the logarithm into a base that you want. Traditionally, most calculators only let you do the natural log or a log base 10, and so it used to be that it was really important that you could change the base into what you wanted it to be, because you couldn't evaluate log base 2 of 3, for example. You would need to change the base into either a log base 10 or a natural log. Your TI Inspires actually do let you change the base, like they let you type in whatever base you want when it's not in press to test mode. So that's great, but this is still a really, really important property and can be very useful. Let's let a, b, and x be positive real numbers such that a does not equal 1 and b does not equal 1. Then log base a of x can be converted to a different base as follows. Let's suppose that I want to change it to just some whatever number, I don't care, some kind of positive real number we're going to call b. I'm going to start with my log base a of x, and then I rewrite it as log base b of x divided by log base b of a. So this is just to say this is true for like any number, including log base 10. So this, what I'm about to write, is actually not anything new. But I'm saying that I can rewrite log base a of x as the log of x over the log of a. I can even rewrite it so that it has a base of e. And we know that a log with a base of e is just a natural log. So log base a of x is the same thing as the natural log of x over the natural log of a. All of those basically said the same thing. They just had different bases. Once again, this is really helpful for calculators if you are not able to actually type in a base that you want. If you can only use logarithms or natural logs. Like let's say you have your phone calculator and you turn it sideways and it gets all scientific. You'll see that there's a log button and a natural log button. It won't let you put some other kind of base in there. So if you had something like this, let's suppose you wanted to evaluate log base 4 of 25. Well, first of all, if I rewrite this as an exponential, I don't know, 4 to what power equals 25? Like that's not a number that I know. You know, if that had been a 16, that would be easy, but it's not a number that I know. So I'm going to want to use my calculator. And in order to use my calculator, I'm going to want to change it to either a common base, which is log base 10, or a natural log base. So common base, I would do log base 25 over log base 4. And I would just like type that in my calculator and it would give me an answer. Or I could do the natural log of 25 over the natural log of 4. Both of those are going to give you the same answer, which is going to be about 2.3219. This last example is kind of more just for fun, but actually the ACT does have logarithms on it. That is one of the things you'll see on the ACT. Hopefully you will find this unit helpful for when you take the ACT. Juniors will take it in April for sure, and then sophomores will take it eventually. But a lot of times they have you rewrite logarithms. And they'll say, like, let logarithm of 2 equal x, and let this equal y. Rewrite this in terms of x and y. So this is kind of like that, except it has numbers. So I'm wanting you to rewrite each of these things in terms of the natural log of 2 and the natural log of 3. For part A, I can see that natural log of 6 is the same thing as the natural log of 2 times 3. And then I can use the product rule. That's the natural log of 2 plus the natural log of 3. That's the answer. This is more of an intellectual exercise than actually useful. Here I'm going to have the natural log of 2 minus the natural log of 27. If I'm trying to write these in terms of natural log of 2 and 3, the first part's taken care of, but I need to figure out how to write that 27. You might be thinking, okay, 27, that's 3 times 9. That's true. I suppose you could rewrite it that way. Maybe I'll do it both. Let's suppose your first instinct was that's 3 times 9. Well, that means the natural log of 2 minus the natural log of 3 plus the natural log of 9. And I'm putting that in parentheses because you were subtracting that whole thing. And then you might be like, okay, well, that's the same thing as the natural log of 3 times 3. And so then you might be like, okay, that's natural log of 3 plus the natural log of 3 plus the natural log of 3. And that's the same thing as 3 natural log of 3's. Like there's 3 of them. Or a much simpler way would have been to start here where I'm circling and say, okay, that's the same thing as the natural log of 2 minus the natural log of 3 to the third power. And then we would use the power rule to move the exponent to the front. And booyah, you get the same answer. Neato. Now we need to do some practice, or rather I need you to do some practice because quite frankly I've practiced this enough. So page 225 to 226. Numbers 7, 9, 11. Then we're going to skip to 45, 47, 49, 53, 57, 71, 75, and 79. I do not think these 11 problems will take you that long. And just so you have absolutely no excuse, I'm going to, I have this picture here for you. This is the first page, so you can see there's 7, 9, 11, 45, 47, 49, 53, and 57. Of course, this would be great for you to just pause the video, and then there's the problems you need to work on. So you could go ahead and pause the video and work on the problems. And then when you hit play, I'm going to have the next page available. Do it. Do the practice. Do it. There were just 3 more problems for practice, number 71, 75, and 79. You're going to be condensing these expressions. So once again, you can go ahead and pause the video and do these practice problems. And that is the end of this video. However, if you would like to see the proof of these rules, once again, I would encourage you to check out page 258 in your book. Or if you don't feel like reading it, just watch my next video.